In the summer of 1977, NASA's Jet Propulsion Laboratory launched a pair of Titan Centaur rockets containing nearly identical spacecraft. Known as Voyager 1 and Voyager 2, these twin probes were built to last for 5 years with the intention of studying Jupiter and Saturn and their larger moons. Incredibly, nearly 45 years later, NASA is still in constant communication with both probes, which take routine commands and transmit collected data back to Earth's deep space network, making Voyager the longest-running mission in the history of space exploration. After completing all of its initial objectives within 4 years, NASA extended Voyager's mission to include the two outer giants, Neptune and Uranus, before embarking on the even more ambitious Voyager Interstellar mission, with the purpose of exploring the outer limits of the Sun's sphere of influence and beyond. Voyagers 1 and 2 have now traveled 22 billion kilometers and 18 billion kilometers from Earth, respectively, so far that they have left the heliosphere and entered interstellar space. But time, even for the long-lived Voyager probes, is running out. Perhaps as soon as 2025, the probes will lose their remaining power supply and go dark forever. In preparation for this, NASA has begun taking the probe's instruments offline, in the hope of extending the life of the mission for a few more years. But when the Voyager probes inevitably do go dark, they will leave behind a wealth of data that is unprecedented in size and scope. So, now that we are entering the Voyager mission's final days, we can ask, what did Voyagers 1 and 2 discover out there? Did the probes and their instruments hold up under the rigors of interstellar travel? And why are NASA scientists so surprised by what they learned? Join me today as we look at the most stunning discoveries of the nearly 45-year Voyager mission and relive the remarkable journey the probes took after they left Neptune's orbit, traveling from the solar system's icy outer giants to the brink of interstellar space. While Voyagers 1 and 2 were supposed to be on a 5-year mission, their team of forward-thinking scientists and engineers made a number of design choices that enabled the probes to hold up over a much longer journey. Each probe is equipped with a long-lasting radioisotope thermoelectric generator, which converts heat from the decaying plutonium-238 isotope into electric power. The probes also have redundancies of most of their 11 scientific instruments in case of machine failure, as well as 16 hydrazine thrusters, including 8 backups. Most importantly, the launch happened at the perfect time. When the Voyager planetary mission launched in 1977, NASA took advantage of a once-in-176-year alignment of the planets, which not only allowed for flybys of Neptune and Uranus with minimal course adjustment, but gave the probes a gravity assist from each of the giants they visited, thereby increasing their effective velocity beyond what they could get from their own rocket propulsion. This idea was relatively new at the time, having been only attempted previously on NASA's Pioneer missions to Jupiter and Saturn. In 1981, Voyager 1 escaped the ecliptic, which is Earth's plane of orbit around the Sun, heading 35 degrees to the north. Voyager 2 later went under the ecliptic, heading 48 degrees to the south. After the Voyager planetary mission was extended to become the Voyager Interstellar mission, the cameras on both probes were deactivated in order to conserve power. The last image taken by Voyager 1 is the famous pale blue dot photograph of Earth, seen from a distance of around 6 billion kilometers, the most remote image of Earth ever taken. However, this was barely the start of the Voyager's journeys. To reach interstellar space, the probes would have to traverse the termination shock, a region in which hypersonic solar winds run into fierce resistance from the interstellar wind. Beyond the termination shock, the Voyagers would encounter the Heliopause, where slowing solar winds pile up, becoming denser and hotter, followed by the Heliopause, the final boundary between the heliosphere and interstellar space. But, in spite of what you may think, the start of the interstellar medium doesn't actually mark the end of our solar system. Indeed, it will be another 300 years until Voyager 1 reaches the Oort cloud, the vast region of billions of icy planetesimals that surrounds our solar system like a bubble, and another 30,000 years until it exits the cloud, leaving our solar system forever. When the Voyagers traveled through the Heliopause, they made an incredible discovery. Because the Sun's magnetic field spins in opposite directions on its north and south poles, the spins create a ripple where they meet called the heliospheric current sheet, sort of like the rings created by dropping a stone in water. However, when this sheet reaches the termination shock, it compresses, as though the ripples were hitting the edge of a pool. The Voyager probes discovered that after the termination shock, these stacked-up ripples form magnetic bubbles. This means the boundary of the Heliopause is not as smooth and clear-cut as scientists thought. Instead, it is a fluctuating and magnetically bubbly environment. This messy finding has prompted a complete revision of our model of the Heliopause. On July 25, 2012, the Voyager 1 space probe became the first man-made object to leave the Sun's heliosphere and enter interstellar space. It was traveling at an incredible speed of 540 million kilometers per year, or 3.6 astronomical units, an astronomical unit being the distance between Earth and the Sun, approximately 149.6 million kilometers. The distance at which Voyager 1 crossed the Heliopause was about 120 astronomical units from the Sun, which itself was a revelation. It was unknown where, exactly, the Heliopause occurred. Funnily enough, some early models put it as close as Jupiter, and others much farther. Remember, the heliopause is the boundary where the sun's solar wind is stopped by its collision with the interstellar medium, kind of like the crashing of two powerful bodies of water against each other. Solar wind is the steady stream of charged particles, such as electrons, protons, and alpha particles, that come from the sun's outer layer. The interstellar medium, by contrast, consists of charged particles, gases, and cosmic dust left over from the Big Bang and from ancient supernovae. When these charged streams hit each other, they change course and form a region of equilibrium, called the heliopause boundary. At first, NASA wasn't sure if Voyager 1 had truly crossed the heliopause and entered interstellar space. As models predicted, the probe's plasma wave detector found a massive increase in plasma density, 80 times what it had registered in the outer Helios sheath, and a spike in galactic cosmic rays. But something strange didn't happen that left scientists baffled. After crossing the heliopause, Voyager 1 detected no change in the ambient magnetic field. Why was that so surprising? Well, theoretical models assumed that the ambient magnetic orientation would change in a region dominated by the magnetic fields of other stars. But remarkably, Voyager 1 detected no discernible change in the ambient magnetism. NASA was so confused that they waited nearly a year before announcing that Voyager 1 had, in fact, entered interstellar space. On November 5, 2018, Voyager 2, traveling at the slightly slower speed of 490 million kilometers, or 3.3 astronomical units, per year, joined Voyager 1 in becoming the second human-made object to enter interstellar space. The crossing also occurred 120 astronomical units from the Sun, and like the Voyager 1 6 years earlier, the probe detected no change in the ambient magnetic field. But something else surprised scientists. You see, the Sun goes through 11-year solar cycles, during which its activity waxes and wanes. Voyager 2's crossing occurred at a time when solar winds were peaking. Models predicted that the size of the heliosphere would fluctuate with the solar cycle, meaning it should have been expanding when Voyager 2 made its crossing. Yet Voyager 2 crossed the heliopause at exactly the same distance Voyager 1 had 6 years prior, meaning our models were wrong. Like the magnetometer finding, this demonstrated the value of testing theoretical models with field data. We now suspect that the boundary between the heliosphere and interstellar medium is much more twisted and filled with fluctuations than prior models proposed. One leading idea is that our Sun emerged billions of years ago from a hot and heavily ionized region following the explosion of one or more supernovae, and that magnetic turbulence persists to this day near the heliopause. If so, the probes will likely encounter a different magnetic orientation as they travel farther away, but their instruments will probably be long dark by that time. Although the historic Voyager mission will soon be ending, the twin probes are just beginning their cosmic journeys. In 40,000 years, Voyager 1 will likely drift toward AC plus 793888, a star in the Camelopardalis constellation, while Voyager 2 will pass 1.7 light-years from the star Ross 248. In 296,000 years, it will pass 4.3 light-years from Sirius. These small, intrepid probes will likely outlast the Earth itself as they continue their solitary wanderings across the Milky Way. And if by chance they encounter intelligent life in one of the far reaches of our galaxy, they will be a testament to humankind's ingenuity and resilience. On each of the probes is a golden audiovisual disc called the Golden Record. These records carry photographs of Earth and its many life forms, the sounds of whales and of babies crying, music by Mozart and Chuck Berry and dozens of indigenous peoples, and greetings in 55 languages. They would offer a distant stranger a glimpse of who we are, and what life on Earth is like. As for us, we must say goodbye to these old familiar friends and continue our own lives here on Earth. Hopefully, the Voyager mission will not be our last brush with the stars, but only the beginning. Incredibly, we haven't just sent probes into space, but SpaceX has even sent a Tesla beyond the orbit of Mars. It made its closest approach of Mars in 2020, at a distance of only 5 million kilometers away. Although it probably won't take you to Mars, if you fancy having a premium Tesla for yourself, Omaze has a sweepstake on right now where you have a chance to win one, and even if you don't, you will still be helping to support the Juju Initiative, a non-profit organization that supports youth initiatives and lifting the spirits of those in need. Thanks for watching. And thanks for supporting the channel through watching, liking, and sharing. It really helps me make more videos in the future. Another way to support is to become a patron or a member so you can have your name added to this list. Check the links in the description below. All the best, and see you next time.